So now that we've established a lot of good math and theory with Young's double slit experiment where, we have two slits, the question's going to come up. Can we put more slits in? The answer is yes, we can always put more slits in. We do not have to restrict ourselves to two. And in fact, this is something that we have access to. So what we're looking at here is we're looking at something called a diffraction grating. So diffraction grating is basically going to be a sheet of glass or plastic, and what's going to happen is you're going to etch a ton of lines into it. So instead of having two slits, you might have thousands of slits. And these are really nice to use in demos with diffraction, with a laser and all of that. So the key question is, okay, well, what's the advantage of having more slits? Like, why is 2 not so great, and why is, like, say, 200 much better? Well, the reason for that is the more paths that we split the light into. So like with 2 slits, we're splitting light into 2 different paths. If we have 200 slits, we're splitting light into 200 different beams. And what that's going to allow, the more splitting of light, the more interference we're having at each particular point. Like if you look at a constructive fringe on the interference pattern in a double slit experiment, that's 2 waves interfering at that point. You have a diffraction grating with 200 slits. Well, at that bright spot, you now have 200 waves interfering with one another. So this is going to have more interference for those slits. And it's also going to be allowing more energy to be delivered at that point on the screen. And then if we want to look at another advantage, we can kind of look at the small angle approximation. And we're going to rearrange it for that distance between our fringes so that x equals lambda NL over D. Now, if we happen to decrease that distance between the slits, what this means is we're having a higher number of slits or lines per centimeter on this diffraction grating. If we start to decrease that distance between the slits or increase the number of slits per unit measurement, if D goes down, X is going to go up, which means that the spacing between the fringes is going to increase. And maybe this will help us with some measurements, like if the fringes are kind of overlapping, well, we get a diffraction grating with more lines etched per unit length. That's going to space out the fringes more, help us with our measurements. Or maybe they're too far away and we want them close together, so then you're going to use a diffraction grating that has a greater spacing or fewer lines etched per centimeter. So if D goes up, X is going to go down, which means that spacing between the fringes is going to decrease. And yeah, if we use one of the other things with diffraction, when we did monochromatic light, or specifically not monochromatic light, when we had white light, if we passed white light through a prism, it refracted into the 7 colors, or at least, the colors, the rainbow. If we pass white light through a diffraction grating, it will also diffract into the rainbow. Now, the order of the colors that are going to be shown is a little bit different, but I'm going to talk about that in the next example because that's going to highlight a really important point. So let's look at an example here. So we want to determine the number of lines per centimeter in a diffraction grating if the third dark fringe is located 5 centimeters from the central antinode when the screen is located 60 centimeters from the grating. Assume lambda is 500 nanometers. Alright, so we have lambda is 5.00 times 10 to the 7 meters. We are told the third dark fringe, so we have x3 is 0.0500 meters, and we're told the screen is located 60 centimeters away. Now, before I do anything, let me check the angle. Because I want to see, if the angle is small, could I use the small angle approximation? So we know the relationship between x and L is that tangent of theta. So theta is going to be that inverse tangent of x over L. So then we have this x value of the 0.0500 meters, so 5 centimeters divided by 60 centimeters, or 0.60 meters. So what's this going to give us? So we got 5 over 60. This is going to give us about 4.8 degrees. The angle is small, so we can use the small angle approximation. So we're justified in using that. Now, we also have the dark fringe. So with the dark fringe, that's going to tell us that lambda is equal to xd over n minus 1/2 L. Now, we're being asked to determine the number of lines per centimeter. We're not being asked to determine the spacing between the slits. If you want to know how many lines there are per unit length, what you're actually trying to find is the inverse of the spacing between the slits. So when we talk about lines per length, what we're actually asking you to do is we're asking you to find 1 over the diffraction grating. Because if I do 1 divided by the diffraction grating, that is going to tell me how many lines we have per unit length. So what we're actually asking to find in this question is we're actually asking to find 1 over d. So 1 over d, if we rearrange for this, 1 over d is going to be, let's see here, it's going to be x over n minus 1/2 lambda L. If you want to solve this for d first and then invert that at the end, that is also perfectly fine. Do what you are the most comfortable with. We don't want you to do a method that makes you, or that puts you at a state of unease. All right, so 1 over d. Let's check. So we have this x. So we're told that this is 0.0500 meters. We're looking at the third dark fringe, so we got this 3 minus 1/2. We got this wavelength of 5 times 10 to the minus 7 meters, and then we have this length of 0.60 meters. So alas, let's just check the units quickly. So I got meters up top. It's going to get rid of a meters on the bottom. So I'm going to have a meters in the bottom here. So this is good. I have an inverse meters. We're on the right track. So let's see what we got going on here. So if I calculate that correctly, I'm going to get the evil number of 6.66 times, or I guess 6.67 with rounding. 6.67 times 10 to the 4. And then the units don't, the lines doesn't come in naturally. We're just going to put this in here. We're going to say that this is, if the spacing between the slits is whatever we have, we're going to say that 1 over that spacing between the slits is lines per meter. So if I inverted this, actually I'm going to just kind of mark this on the side here. If we solve for d, we'd get d is 1.50 times 10 to the minus 5 meters. So that is the distance between the slits. If I want to know how many slits are in a meter, knowing that each slit is that distance apart, what I'm going to get is I'm going to get 6.67 times 10 to the 4 lines per meter. So with that spacing being about 1.50 times 10 to the minus 5 meters apart, what that means is if I had a diffraction grating a meter long, I'd be able to fit about 66,667 lines in that diffraction grating. But the only thing, and this is where the diploma likes to get people, we have lines per centimeter. So we actually don't want lines per meter. We need to get rid of that meter. And this is also where students do the conversion incorrectly, because they say, okay, well, meters, I know there's 100 centimeters in a meter. And then so what they're going to end up doing is they're going to be multiplying this by 100. Be careful though, the meters are in the denominator this time. So the meters are in the bottom, we want a meters up top, and we want a centimeters in the bottom. And we know that there are 100 centimeters for every 1 meter. So we actually have to divide this thing by 100. Really be careful with your units here. So all that's going to do is reduce this power by 2. And then actually, I guess for sig digs, technically I only have 2 sig digs in this length here, so I actually have to even round this some more. So I could say that the spacing in this slits is about 6.7 times 10 squared lines per centimeter. So the big thing is anytime you're asked for lines per unit length, you're finding 1 over the diffraction spacing. You're finding 1 over d. Just check to see what units they want that in. If it's lines per centimeter, lines per millimeter, lines per meter, especially in a numerical response. Always check the units. So the last thing I just want to talk about to wrap up diffraction is I want to talk about this common diploma example. This gets asked in many different ways. It's usually asked on every diploma, and it's basically to see if you know the difference between white light diffracting versus white light refracting. So we have white light incident on a diffraction grating, and it's also incident on a triangular prism. So in this case, we have diffraction, and in this case, we have refraction. So we're being told we want the colors at positions 1, 2, 3, and 4. So we talked about in refraction how red light refracts the least and violet light refracts the most. Now, I have red and blue as my choices. Now, blue has a smaller wavelength than red, so instead of violet, we're going to say blue refracts more. But let me get to that in a minute. Diffraction, it's going to be kind of the opposite. For diffraction, what we're going to find is that violet light diffracts the least and red light refracts the most. Now, students have to try and remember this, and people always say, well, how do you remember this? Well, a friend of mine who was also a physics teacher, she taught me a really cute saying. It's corny as hell, but every time students do these questions, I see them write it out on the exams. So it may be corny, but people remember it. So we're going to put this saying in here. Bear with me. So we're going to put this very dry lips require red lipstick. Now, I don't know whether dry lips require lipstick or not. I can't answer that question. But you might say, Mr. O'Donnell, what is this? This is nonsensical. Fair enough. Bear with me for 2 seconds. So if we can remember very dry lips require red lipstick, you'll notice I've capitalized the first letter in each word. So V, the first V is going to be violet. This D is diffracts. L, least. Red refracts least. This is meant to tell you what diffracts the least and what refracts the least. So from very dry lips, we can see that violet diffracts least. And then for refraction, red refracts least. Very dry lips require red lipstick. If you can remember that saying, you'll nail these questions every single time. Now, what that's telling us is that the light with the lower wavelength is going to refract the least. Between our choices of blue and red, that tells us that's blue at this position, which means that red is going to be up here because it's going to diffract the most. Now, for our triangular prism with refraction, red is going to refract the least, which means that blue is going to refract more. So we're looking for something with red, blue, red, blue. Well, red, blue, that is going to be A. And like I said, you may not get this exact question. In fact, you probably won't get that exact question, but it's very common on the diploma to ask you to distinguish between the refraction of white light versus the diffraction of white light. So like I said, if you can remember very dry lips require red lipstick, you are good to go. So I do have to thank my friend, Miss Ing. She is the one that taught me that. So good on her for thinking of something this corny. So yeah, remember that for the diploma. It gets asked all the time.